In this example, we're going to find out the region enclosed between two curves, which is shown in the diagram as shaded grey. Then we're going to take this region and rotate it around the x-axis. To solve this question, what we need to do is firstly find out the points at which the two curves intersect. So we're going to find out the points of intersection. For the points of intersection, that is where one curve equals the other curve. So I'm going to say x squared is equal to the square root of x. Here we need to solve for x, so I'm going to square both sides and get x to the power of 4 is equal to x. Grouping onto one side of the equal sign, I get x to the power of 4 minus x equals 0, which we can now factorize. X times x cubed minus 1 equals 0. That tells me x is equal to 0, or x to the power of 3 minus 1 equals 0, which tells me x equals 0 or x is equal to 1. So we know when x is equal to 0, y is also equal to 0. We know when x is equal to 1, y is also equal to 1 by substituting into the formulas. So what we have now is 0, 0 and 1, 1. The first thing we need to do when we're finding the volumes of revolution is we need to look to see which curve is on top. In yellow, I have just highlighted the curve that is on top in the region that we're interested in. That is y equals the square root of x. The curve that is underneath, I'm going to mark in green. That is y equals x squared. So what we need to do is we need to work out the volume that is under the curve y equals root x when it is rotated around the x-axis. That will give us a volume, but that's the total volume between 0 and 1. From that, we subtract the volume that is generated when we rotate y equals x squared around the x-axis between 0 and 1. My volume is going to be the curve that is on top, so pi times the integral from, we found x is 0 to x is 1. We know that our curve was on top was root x, which we're going to square dx. From that, we're going to subtract the volume that will be generated when we rotate the other curve around the x-axis, that is y equals x squared. So we're going to have pi between 0 and 1 of x squared all squared dx. Expanding that, that gives me pi between 0 and 1 of x dx minus pi 0 of 1 x to the power of 4 dx. Looking at our two expressions, you can see that they have the same integral in 0 and 1. You can also see both are multiplied by pi, so I can combine these. Firstly, the pi I'm going to take out as a common factor. Using your rules that you learnt in maths methods, the terminals are the same for both integrals. So I'm going to write 0 to 1. And we now have x minus x to the power of 4 dx. Now we're going to anti-differentiate. The antiderivative of x is x squared on 2 minus the antiderivative of x to the power of 4, which is x to the power of 5 on 5, between 0 and 1. Substituting in, I get pi times 1/2 minus 1/5, minus, substituting in the 0, it all comes to 0. That gives me 3 pi on 10 cubic units. Question comes, why didn't we combine those together originally? If you consider v equals pi integral fx minus gx all squared dx, if I expanded that bracket, what I would get would be fx all squared minus 2 times fx times gx plus gx all squared. If you compare that to what we have with the original formula, that original formula is v equals fx squared minus gx all squared dx. You can see that the two are different.